Sam's been doing this for ages.
Yeah.
So those, I'll email you those two things, and if anybody has any questions, otherwise, tomorrow, if I'm not here right at 8:30, I'll check in, at 9-ish also.
Just real quick about the Exceed conference in July. We told Exceed that you would have 6 weeks of a project. So it's a project of work to present for those of you who will get to go to Exceed. Actually, you're going to be heroes, so you all get 5 weeks to get something to show work in progress. So they know that it's work in progress. Depending on how far along you are, it will determine who we can add those since we're going to pay for everything for the conference and the funding. I think right now we have funding for 5 people. We're trying to get more for others. So some of you might get the travel award, so we need to know that. But just be aware of your time. Because we're going to have you come up with a statement of work. If you're probably more of a work-oriented project or a research.
That's the one right out there, huh?
So it depends on what you want to look like. And make sure you stick to that.
Yeah.
Like the timeline is at 5.
Do you want me to try and get them on the 3:30?
If you want to have a decent presentation, we're not going to let you go if you're not. We're not going to
Whatever you've had.
embarrass themselves.
Okay.
Because if you've had enough, they've had
Because you
enough.
have time after that meeting, you can come back and continue working on it. So people will know that it's in progress. Because there's going to be training there. They have tutorials that you can take there. We'll present a poster. There's a session that we're doing for people about recruiting students to RAU, and some of you will talk about how you were recruited. What worked, what didn't work for RAUs. So we'll keep you posted on that. Things happen pretty quick. It seems like it's a long time, but the time goes by real quick. People should slack off in the beginning when they get crunched. Even though you need to take advantage of the full time that you have to work all day, because that's what you're getting paid for. So be aware of that. If you think that, I've got time, you don't. So you're going to need a roadmap. We'll get you that statement of work or the research plan guide. We'll be talking more about Exceed.
I gotta get a Johnson.
What's that? Yeah, just initial next to the little hyphen there. Not hyphen, it's an underscore, it's an underscore right there.
Where do we get the shuttle for tomorrow? Same place?
So same place, there's only one stop on campus that brings you to the pickle. And then when you're done with training today, you want to make sure you go out and then and actually, John will let me know, and then I'll walk you out or show you. It's very easy. We'll go out through this front. Is it the same? They get dropped off over here, but they pick up on this side, right?
No, they might only pick it up in front of Commons now.
Really?
Yeah.
Oh.
Yeah, they went down to single stop, I believe.
Really? So
Mhm.
that's where they have to go back wherever they got dropped off?
Yep.
In front of Liverpool?
So today, wherever you got dropped off from the shuttle, that's where you're going to pick up the shuttle.
Right out in front of the cafeteria.
Yeah.
It's a block.
And then remember to note on your calendar, if you haven't RSVP'd for that reception through the scholars, make sure you do it by tomorrow.
Wait, what?
So, there's that, in that yellow packet, there's a flyer for a reception that takes place, I think, on the 11th or 10th. Yes. So just make sure you go to that you RSVP by tomorrow.
Where is the shuttle tomorrow? We go to
Oh, no, it's going to drop you off. When it drops you off, just like today,
Yeah,
you get
that's fine.
training, and then you're going to get it off, pick up the shuttle, you get dropped off where it drops you off. There's only one place where it picks up and drops off on campus. And that's where you're going to walk to the AT&T Conference Center. But our AT&T Conference Center is on campus.
Yeah. I'll just walk.
We'll be starting in just a few minutes.
On your training agenda? Oh, so we had to get you out of here by, right after lunch, or if you're trying to leave here by 1:20. He's got to leave here at 1:20 tomorrow to get to a meeting with his research team at 2 p.m. And ask him, and I'll text him. You want to merge and be part of that research team. No, Ricky was not part of the research team. Some depends on the faculty. Like, Zach's research team. Zach, you know, but your research team has a good, like, 4 students, 5 students. Yeah, but it just, usually it's between 2 to, you know, I'm not sure how many people. How big is your research team with Dr. Wow. See, that's pretty big. No, researchers in the lab, there's like 20, but in my. Okay.
It is recording. It's actually on a Google Hangout.
5 researchers on that.
Yeah, so tonight, if you go to the Google Plus TAC page on Google Plus, you'll see there's an afternoon and a morning session for each set. You can go back and rewatch these. Yeah, it'll all be up there. This whole recording. What's that? I did, yeah.
I have every faculty language, so that's why they're because they're easier to read.
There we go.
You know how that is.
Yep, you can find us on Google Plus, just Texas Advanced Computing Center. You can follow our circle us, whatever that is. You can +1 things.
Yeah, I'm gonna go ahead and follow.
You can go back and ask questions. Somebody may answer you. I try to watch it as much as I can.
Let me find out. I think she lost her researcher. Her graduate student who is an exit process. Sam, you know Dr. Booth, she was the one that lost the graduate researcher? Or was transitioning, graduated?
Where it's gone already, but yeah.
Okay. Okay, so that's why. So I'll follow up with her and make sure that we schedule a meeting. We'll do that. I'll do that right back. Yes. With your research, Dr. Booth? That one should be posted on the website actually, on the ICERT REU. Right? Is that what posted on the website, the project description?
No, all the descriptions are posted.
For Dr. Booth, which one is yours?
Yeah.
Okay, let's send them the statement of the project. Okay.
Yeah, for you to look at their research, you're not, you'll probably be doing just a part of that. And for some of you, they might have you doing something else. Because they want you to come to the organization. But Dr. Lou will be actually expecting.
Can I get this?
Yeah.
Which was the only one that I need to make sure we.
I'm thinking something. Because when I applied, I was told that somebody put a couple of.
It's just initial, just to make sure that you know that I went over those items this morning.
Yeah.
Thank you.
I searched REU.org.
Are we ready to rock? Everybody's ready for a fun-filled afternoon session?
Yeah.
Yeah!
There's snacks in the back of the room in case anybody needs to,
Yeah, we have snacks and cookies and more caffeine.
Yes, to make sure we don't.
It's gonna.
There you go.
Be in transit.
Snack up. Yep. Get some food.
Thank you.
Oh, we'll take a break too in a few minutes. Well, 45 hour. Maybe.
Did you go to UT?
I'm sorry?
Did you go to UT when you were in college?
I did not actually. Went to Texas A&M and Corpus Christi. And I did do a year here at UT Austin as well.
Okay.
For fun.
I was gonna say undergrad or like a master's degree or. Computer science, like computer engineering.
Computer science. Yeah. And then I turned into functional computing. What's that? Not one of my favorites.
Not mine either.
Also, not a great language for supercomputing, as it turns out. It's very heavyweight. It requires a lot to run the Java virtual machine. It's very nice that you can run it on anything, but it runs everywhere slowly.
Yeah.
All right, let's go ahead and get started. I just wanted to finish up the Linux lecture with a little brief introduction to regular expressions, because they're really neat. It's something you should be exposed to, at least to see it and see how it works. And I have a little example. We did have one computational biologist, right? Biochem. Okay, that's close. So I have a sequence analysis output file, so we can kind of play around with it, and I can show you a couple of techniques as we try to chain all these together. We'll do this brief introduction of regular expressions, and then we'll actually talk about the Stampede system and how we're going to get on there to actually run some codes. So I always like to start my regular expression code with this quote. Some people, when confronted with a problem, think, I know, I'll use regular expressions. And now you have two problems. So what exactly are regular expressions? Yes, I have. Yeah, the broadcast is live. We have people on the internet that are watching this as well. They can only see me, they can't see you. You can watch this later. If you go to the Google Plus, TAX Google Plus page, so just go log into Google Plus and search for Texas Advanced Computing Center, you will find our page, which has all of these videos, including this morning session was recorded in a morning and afternoon video segment. So you can always go back and go, what was it that he said again? Because he didn't write it in the slides, but he said it like 6 times. So you can go back and find that. And skip around, it's like a YouTube player. Yeah?
That's what I was on thinking about.
Yes, everything's in there, and I believe it's picking up my voice pretty well, so I haven't heard any complaints yet. So what are regular expressions? They are a concise grammar for doing pattern matching in strings or text. That's just the basics. They're often abbreviated as regex, because people, again, don't want to write out the entire word of regular expressions. And basically, what we can do with regular expressions is we can describe search patterns, which can be very useful if you're trying to, say, sift through a mountain of text-based files, which we often have to. So we call a regular expression a pattern, and it's just going to describe a set of strings. So I've put in some very basic examples here, and again, you're not going to walk out of this and know everything about regular expressions or how to do really complex things, but I just want you to be exposed to it so you can see it, and when you do see this problem, you go, oh, wait, I know there's something that does this for me. So there's we're typically using these to give a concise description of a set without having to list all the elements. So for example, I have the word handel represented in 3 different strings with the proper umlauted A, the American English version, and the English version that actually takes care of the umlauted A by putting the AE in there. Now, all 3 of these are correct, right? So if I wanted to write a regular expression that would match all of these, because I say, well, that's fine if you use the umlauted A or the non-umlauted A, it's fine, we'll pick up all of them. You can write a pattern like this, something that starts out with a capital H, and then I have a grouping here, which says it could be an umlauted A, the pipe means or it could be A, and it could possibly have an E. That's what the question mark means. And again, I'm going to show you these, and we'll start to go over a little bit more thoroughly in the example. But basically, this is a simple regular expression that I can write to represent all 3 of these strings. Why do you care about regular expressions? Well, if you're using Linux, as you guys are, they're everywhere. We can use them in a lot of programs, including grep and egrep. We're going to do a grep example today. You can use them in sed, which is a stream editor that allows you to find a pattern in text and then transform it into something else. Maybe I want to look for all instances of the word foo in this file and remove them, or change them all to bar, or something like this. You can use regular expressions with the find command that we saw earlier today in this morning's lecture. You can use them in awk, which is a data extraction and reporting tool. We'll do a little bit with awk today, and probably a lot more of it tomorrow in the shell scripting session. You can use regular expressions just in your bash shell if you want to do interesting listings and things like that, and of course with ls. So some of the basics of regular expressions: you have the pipe operator, which is an alternation or an or. You have the question mark, which is an optional. As you saw in the previous example, it was E question mark, meaning that it could be in there or not, doesn't matter. And then you have the other operators, the asterisk, which means 0 or more. Match it if there's none of them or if there's a ton of them. And then we have the plus, which is 1 or more, meaning that at least one has to exist. Yes? Sure. So the Boolean OR is just a single pipe operator, the bar, and that's just used to separate alternatives. So, for example, I could have gray spelled in American English and UK English, either spelled with an A or spelled with an E. To me, I don't really care. They're both syntactically correct, right, in this example. So we could do something like gray or gray. As a matching string. In this way, I actually wrote the whole thing out, and that's kind of, well, that's kind of a bummer, but I could instead use grouping, where I could say, this would be a lot better if it was on a new line. Let me fix that for you. We could do this instead, where we could say, instead of doing gray or gray, we could say gr, and then use the parentheses to group these operators and say it could be an A or an E followed by a Y. So this is the way we have a nice little pattern that can describe the set of both gray and gray. The quantifier tokens or group specifies how often the preceding element is allowed to occur. So the most common quantifiers that we'll use is the question mark, the asterisk, and the plus sign. So the question mark indicates that there's 0 or 1 of the preceding elements, meaning that either it could not exist or there must be at least one. So an example of this may be, again, American English versus UK English. We have color spelled with a U or without a U. Both, again, are correct. It doesn't matter to me which you use. So an example of this, we could spell it C-O-L-O-U question mark R, meaning that this U could exist but only one time. The asterisk indicates that there can be 0 or more. So if I had something like A, B, star C, this could be just AC, the pattern, with no B in it. It could be A, B, C, so I have 1. It could be A, B, B, C, I have more, and A, B, 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 C, and on, because the asterisk, again, 0 or more of the preceding element. The plus sign is an indicator of 1 or more of the preceding. So this is the one that says, well, I must have at least 1. So it will not, as in the previous example, will not match just AC. There must be at least 1 B, and then there can be as many B's as you want in the middle. You also have a handful of meta characters that you can use. The full stop, the period. This can be used to match any single character. So we can represent any character with the dot. So in our previous example, we could say A.C, which could be ABC. It could be anything else in there in between, any other regular character. Now we can also use brackets to match a single character that's contained within the brackets. So we could do something like bracket ABC would match any of those, if there was an A, if there was a B, or if there was a C. So it can get kind of complicated as we start to build these, but you'll see kind of how we use these later on, especially tomorrow when we get to more shell scripting. You can use ranges as well. You can say, oh, I want all the lowercase characters A to Z, or maybe I just want numeric, 0 to 9. So this is a nice way where you can do a lot of different types of pattern matching inside and just kind of represent a string in many different ways. The other meta characters that we might use, we can use the caret inside of a bracket. This matches a single character that's not contained in the brackets. So if I said something like the caret ABC, we'd say, okay, make sure that A, B, or C is not in the string, which is, we do want to do that a lot. We want to look for the negation. And just the caret by itself, interestingly enough, matches the starting position within the string. So if I don't use the brackets, I just say, oh, something like caret foo, it's going to look at the beginning of each line, and if the first thing in there, that string is foo, then it'll match that. Alternatively, if you want to match something at the end, so maybe you know that the strings that you're looking for end in a certain character or a string of characters, you can use the $sign. So we could say something like $AT would match any word that ended on the line with like hat or cat, but only again if they're at the end of the line. So remember the caret is at the beginning and the $, is at the end. So that's it. That's all I wanted to show you. There's regular expressions. You're going to probably use them, and those are just some of the stuff. And again, I'll give these slides to you guys so you can look through them later, but there's a lot of good documentation online about this as well. But let's take a look at grep, which is a nice program included with Linux that allows you to search the file that you give it looking for a certain pattern or lines containing a pattern that you give it. By default, when you run grep with a search, it will print the lines that match. So if I say maybe I have this huge text file and I just want to print every line that contains the word foo or the word bar, we could say grep for foo in this file, and it will print out all the lines where that's true. So you might have an example like this. I have this blast output file. And if anybody has used BLAST before, you'll know that it tends to put out very large text files. So large that you wouldn't want to open it and read it because one, will take forever to try and open it, and then once you're into it, you're not going to get any information out of it. You really need to sort and get the information out of it exactly how you want. That's what we're going to do in this example. So maybe I wanted to, for instance, find all of the lines containing the string May 6th. So I'm just going to use some simple string patterns in this example so you can kind of get a feel for how it works. So I'm looking for everything that says May 6th in this file called example.txt, and the file looks kind of like this, where it might say, hey, this is the database I used, this was the date that it was posted, number of letters in the database, number of sequences. You can apply this to a lot of different things. But basically I say grep out for May 6th, and what it does is it'll only print that one line, right, that says, okay, posted May 6th. Maybe not so interesting for this, but we can start to do some really cool things. After we grep stuff out, we can use this program called awk. And awk is actually a language. It's not a huge language, but it's a very useful tool. Again, I'm just going to kind of present it to you here, and then we'll talk about it more in depth tomorrow during the shell scripting and possibly towards the end of the week as well. If we want to find information, of course, check out the man page. So just man awk. It's got a whole lot of options and things that you can do with it. Basically, it's a pattern scanning and processing language. And what I use it for most of the time is just to print out specific columns of data. So the print command displays the contents of the current line. Lines are broken down into fields, which are separated by default, I believe it's a space. And you can change it to whatever you want. Maybe you have comma-separated values. Maybe you have values that are separated by a tab or values that are separated by some special character. You can give awk an option to say, hey, I want it separated by this. But what's neat is you can just do things like print $1, which is print the first field of the current line. So again, maybe I have some columns of data in here, and I say, well, I don't want to print the first part because there's no good information in there, and the second part is actually like my score or the result that I'm looking for. So you can do things like print $1, print the first field. You could say print $1, $3 would print the first and the third fields of that line. Again, there's the columns are auto-separated by a single space character by default. They call that the output field separator, if you're Googling around trying to figure out what that is. So for example, I have a file that says something like this. Foo1 bar baz, foo2 bar baz, and then it keeps getting longer and longer. And maybe I'm just going to cat this file and pipe it to awk. So again, we're going to go back to our previous examples where we're going to use pipe and we're going to keep chaining together a lot of these commands to get the result that we want to do. So I could just say cat example.text, and of course that would just print this out to the screen, right? But instead I'm piping that output into awk and saying just print $1. And so what it does is, because they're separated by a single space, it only prints that first value every time, foo 1, 2, 3, 4. Pretty cool. Another very useful program that we use a lot called sed, and this is a stream editor for filtering and transforming text. So you can do, again, same kind of thing here. We can search through an entire file very quickly and replace all instances with a single call. So in this example, I have my program called myfile.txt, and I want to find every instance of the word foo and replace it with bar. That's what the S is search and replace. And we say anything in between these slashes, search for this, replace it with this, and then I added a G on the end which says do it globally, meaning that anytime you find an instance of this word, replace it with this other word. And this can be really useful, especially if you got very large files and you just want to change one thing real quickly in all of them. You can say go through this whole file and replace all of these values. So let's put some of these things together, and we'll chain together a bunch of stuff and try to find some good information out of this file. So I have this blast output file. It's pretty big. I think it's about 5 gigs. It's much larger than you would ever want to open and read, because there's just a ton of text in it, and there's not really much you would get from it just reading it. What I'd like to do is I'd like to look for this high-scoring hits is what the blast uses, and so I'm going to say let's look for hits that are higher than 300. A score is higher than 300, and we'll use a combination of grep, awk, and word count that we saw earlier today. So the first thing I have is how many scores were there actually total, and so what I did was I said grep for the word score from this file and pipe it out to word count. So I can do this. I have this file here on Stampede in my it's in my Scratch directory. So we can say grep the word score from this file and pipe it to word count -L. Right? Is that all I wanted to do? It is. I do this, and it's going to take a while because this is a big file. Like I said, it's about 5 gigs. And again, I can't really read it to find any useful information out of it. While that's running, we can continue on, but because I already counted this, there's over 5 million results, right? And that's not really useful to me, right? I can't really look at 5 million results. I might be able to plot it and maybe do some things, make it look nice, but I really want to break it down a little more to get information that I'm really looking for. So what I might do is let's make use of awk now, and we'll say we'll grep for that score, that same word score in that file, but instead of just word counting it, we'll pipe it out to awk. Take a look at the third column. So we're going to say, let's say if the third column is greater than 300, then print. And then when we print it, I don't really want to look at them. I'm just going to pipe it out to word count, and then we'll see how many hits we get there. So there we see it. It did complete, and again, it took about a minute to get that through because it's a big file. It's exactly 5 gigs. So yeah, kind of a big file, kind of hard to get through there. So let's take a look at. We'll do that same grep. We're grep for score, but this time we're going to add in. We're going to pipe it out to awk, right? And bring up a quote, and we'll say the third column is greater than 300, then print. And instead of putting out to word count, I'm just going to pipe it out to head, so I see the first 10 results. Make sure I'm getting the right information here, and make sure that I have all of my quotes closed. So now we see I'm looking at. Remember I said $3, so this is the first column, $1, where it says score. The second one is separated by a space, is the equal sign, that's $2, and then this third number here is my the third column, my score. So again, I'm just saying, hey, if that value is greater than 300, and it looks like all of these are, then let's count them up. So instead of piping it out to head, let's pipe it to word count minus L so we can find out how many lines we find with scores that are higher than 300. And as that runs in the background, again, it's going to take a little while because it has to read through that whole file, we'll find that there's 317,983 results. Again, maybe still a little much for what I want to do. I want to really dig down and get a little more. So I put all this information here, so when you look back at the slides, you can say, hey, this is what each step did. We looked for scores of over 300. We grep for the word score. We used awk to look at the third column. Look at that. I can fix it right there. To look at the third column, the three end. Perfect. Third column from grep's output, determine if it's greater than 300, and if it is, it prints, right? And then the last part, we pipe it out to word count and say, hey, how many did you find? And if we go here, we see, cool, we did find a lot of results. And I think still a little much for what we want to do. So, so let's make our query a little more refined. And this time I'm going to search specifically for instances of this special plant that biologists like to use, the Metacargo truncatula. It's an awesome little leafy thing. It's easy to study, so they use it a lot. So what we'll do is instead of just looking for score, we're going to look for these exact instances, because I know that the way that this file is organized is it has scores, but then it also has, well, here's this specific plant or well, whatever it is that we're looking for. So we'll look for just those examples, just this plant, and then we'll say from this file, we'll pipe that out to another grep, but this time we're going to grep minus V, which means if you match it, don't show it to me. It's kind of the anti-grep, right? So grep minus V, because I know that there's duplicate entries in this file, that they start with this character. So again, I know a little bit about this file. I know how the output is, so that helps me to determine what I'm going to write here. But we're just going to look for that. We're going to remove any of the duplicate entries, and then we just word count that. So we'll get rid of that. And instead of score, we're going to grep for it's capital M and then an underbar. I think I spelled that right. Looks like it. And as that runs, I can tell you, again, still about 300,000 entries for just that one plant. So again, still maybe a little, you know, I'm doing a better search now. I'm not just looking at all the scores. I'm looking at a specific score. But again, it's still a little much for me to look at. So let's try to get this down a little bit more. So I'll look for oh, and you notice this too. I said there's 302,000. When I did this, I got 500,000 results, right? Why is that? I forgot to get rid of the duplicates. So we can put that back in there. We'll grep minus V for that character. Pipe that to WC. That should give us the correct result. Excellent. I like it when things work. So this time, let's say we'll look for the instances of this plant. We'll remove all of the duplicates, and then we'll also check to make sure that the score is higher than 300. So that's what we're doing here. Again, we're going to look for instances of Metacargo truncatula in this file. We're going to pipe out every instance of that to another grep that says, if it starts with this character, just throw it away. We'll pipe that output into awk, which says, hey, look at column 2, maybe. We'll have to look at that. We'll have to make sure that that works. If it's over 300, then print it. So let's go ahead and add that in. So again, I'm just going to use my history. So when you're on the Linux machine here, if you just hit the up arrow, that goes through your history as well. Remember earlier I showed you the Control-R for the reverse intelligence search. I use the up arrow a lot, especially if I'm just going to rewrite the same command, or maybe just modify it a little bit. So we're going to get that. We're going to pipe that output to awk, and we're going to look $2 greater than 300, then print. And again, instead of piping this out to word count, I'm going to pipe it out to head just to make sure that I'm actually looking at the right data. And so it does look like that the way that this area of the program set up, the way it writes it out is here's my metacognitive calcula, and here's my score right here, which is actually column 2. So that's good. So we're going to go ahead and put that through word count. And when we do this, we should see that we get less results, which in this case is going to be better, because it's something that I'll actually be able to work with. There we go, 15,000 results. A lot better than 500,000, right? I mean, I could plot that many points, but it might not make sense. This really allows me to really drill down into the output file and just pull out the little pieces that I want. And really all I'm doing is piping together some very simple Unix commands, right? So pretty neat. I just wanted to expose you to some regular expressions so you can see what it's like. And again, you can go back to that quote that when you find a problem, you go, oh, I know that I could use regular expressions. Now you'll have 2 problems too. There's a lot of stuff, again, presented in this first part. So don't feel overwhelmed. Pick up a book on Linux. There's a lot of good web resources out there too if you want to read. There's a ton of people out on, believe it or not, IRC chat rooms are still available for support, especially with scientific libraries. You'll see people out there that are just hanging out, and if you ask a question, they'll probably answer you. So you might take a book on regular expressions too, and you can generate a lot better queries, you know, so you can keep searching through all these large text files. So that's that. Now let's finish up this afternoon here. Not the lab. That was close, but maybe I don't have it open. There we go. So now I want to talk specifically about the Stampede user environment. Why is this opening all funny? So we know a little bit about Linux now. We can make files and stuff. Has everybody picked an editor over lunch? How many VI people? All right. How many Emacs? No Emacs. How about Nano? I didn't even talk about that, but we have that too. No, Nano's a lot easier. Promise. And you'll probably want to take a look at that one to get us started. Why isn't this full screened? There we go. All right, so let's talk a little bit about the user environment, and then we'll start playing around with our editors as well and trying to get you familiar with maybe writing a couple of text files, and we're going to submit a job to Stampede. Pretty cool. So basically, our philosophy here is that effective users are good citizens on our machines. So we're going to talk about how to access Stampede, and I think a lot of us are already on there, but I want to get you acquainted with the machine itself, and so you can kind of know a little bit about the hardware, what's available, and what's available to you. We'll also talk about how to get work done using Stampede, which I believe most of you guys are going to be using Stampede for your research this summer, so this is directly applicable to you guys. And we'll finish up with getting along the good citizenship side of working on here. And then what we'll do is we'll do a test drive for a lab to finish off the day here, and I'll do a quick tour of the mic as well while we're talking about that. You probably don't know what I mean when I say the mic. On Stampede, we have an innovative portion of the machine that is a new technology that was created by Intel called the Intel Xeon Phi coprocessor. This is a 61 cores on a card in your PCI slot. And they're regular old x86 cores. So the code that you write and compile on your regular machine, you can actually run right there on those Xeon Phis too. And the cool thing about them is they take advantage of a lot of parallelism because they have so many cores. Disclaimers. Yeah, these are for people who are new to supercomputing. That's you guys. I try to go breadth rather than depth, so we try to cover a lot but not go too deep into it. We can always do that afterwards. And of course, Stampede is a moving target as several things are pending and evolving. So things will change, but for now, these all work today, and we'll do the lab and we'll have fun with it. For other information that you might want to look for when you start doing this, you can take a look at just standard Linux, Unix general manuals or things online. If you're looking for help with specific applications and programs, you might first try their forums or their IRC chats. Of course, we do have a ton of experts here at TAC as well who can give you help with the environment in general, talking about the batch system, how the tape robot works, the Xeon Phis, these sort of things. And of course, we have lots of advice for computing in general. We covered this, but I like to hit it over and over and over. Remember that the manual page is out there for you. You can find all sorts of examples and templates and cheat sheets online as well. Now, one thing that we have here at TAC is this system called modules, and we're going to talk about that in a little bit. But basically, we have pre-built a lot of the software that you'll want to use on Stampede, and it's available through this module system. We'll walk through it today. But always, like I said, check if there are web pages about the software you're using, user forums. Somebody at TAC typically knows about these things too, so you can always submit a ticket through the portal. So if you just log into the TAC user portal and you say, hey, I'm trying to run this thing, but I don't know how to use it, there's somebody that'll help you out. For more help with the environment at TAC, of course, read the user guides. We do provide them for you so that you have lots of information out there. Always take a look at the updates and notices at the top of the user guide, because we'll tend to put things in if something changes or we change compilers or something like that. We try to put it in there. You can also submit a ticket in the user portal, like I said. So if you go to our website, tac.utexas.edu, you'll find under user services the user guides. And we have a guide for each machine that we have here that we operate. So Stampede is one that you're probably most interested in. You can take a look here, and again, there's updates and notices right at the top that says, hey, you can only use these for certain things, new queue policies, stuff like that. It's organized right here on the side, so you can kind of look at, how do I transfer files? Okay, cool. There's some information that I showed you earlier, how to SCP, how to use rsync, that kind of stuff. So you can always refer back to our user guide for a lot of that information. No. And I lost my presentation. Okay, we'll try it again. Yeah, one other thing, like I said, you can always submit a ticket for advice. We love doing this stuff. That's what we're here for. So we're always happy to talk to you and think about your application or what it is that you're working on. So don't feel afraid to ask questions. That's what we do. So let's talk a little bit about access to Stampede and other TAC resources. Of course, you guys know that before you log in, you do need a portal account. And fortunately, everybody has a portal account right now. Everybody's tied to an allocation for this class. It's called 2014 REU. And basically the way that works is that's what gives you computing hours. So that's what allows us to log into the machine, and that's what allows us to use the compute resources as well. Typically the way this works is your PI, your primary investigator, principal investigator, will request an allocation through the portal. So whoever you're teamed up with for your research team, they probably already have an allocation, we hope. And then they can use the portal to assign active users to the allocation, just like we did to you today. We added you all onto this training allocation. They're associated with the project name, account code. You'll see it when you log in. So you remember when I log into Stampede, I get this nice message that shows me all of the, maybe if I make that a little smaller, shows me all of the allocations that I'm attached to. So you can see here's maybe my training allocation. Here's the one that we're going to use for this class, 2014 REU, and it shows us our available SUs as well, and in this case we have 5,000 SUs available. So 5,000 hours divided by 16 because there's 16 cores on a node. And why do I keep losing my presentation? There we go. We've all been through the activation process, but so you know when you go talk to your friends and you go, hey, go get an account on TAC, you can tell them exactly what you have to do. Right, first thing you do is request that account. You have to verify your account with the email, and then we get you on the machine. It usually takes a few minutes to actually propagate those accounts over, as we saw today. But basically, to start off, as we've already done, we've all logged into Stampede using SSH. Linux, just use your terminal. Mac, use your terminal app. For the Windows folks, there's PuTTY and Secure Shell Client. And there's a couple of other options out there, but those are the two that we'll tend to stick with. And of course, this is how we connect to the login node. Just SSH over to the machine, or as I showed you guys earlier, SSH with your username at the machine. That way, it doesn't assume who you are, and you can skip one step of it asking you for a username. I have these other options here: SSH minus X and minus Y. This is if you want to do X forwarding, meaning that you might run some graphical code from Stampede. You would need to use the X or the Y. Maybe if you're using the debugger DDT or something like that. We talked a little bit about shells and startup scripts. We do have several shells available. Bash, again, is the default. We do have Z shell installed for those who are really interested, and C shell and TC shell for legacy's sake, I suppose. You can, of course, just submit a ticket to change your shell. No big deal. It happens pretty quickly. And as you saw earlier, change shell does not work on Stampede. There's several system-level startup files that execute before your actual startup scripts run. So it is worth your while to understand some of the startup files. You know, we talked about the .profile and .bashrc. There are easy ways to customize your environment, as I showed you how to change my prompt so it looks a little different, how to set up aliases so you can say, oh, every time I run ls, just always run -LTR, or always turn colors off, or something like that. You do want to be cautious, though, because your environment is associated with that shell, so if you don't want to mess anything up in there, and definitely avoid using the echo command in your startup scripts, because it will break other programs like SCP, which are not expecting an echo when it starts copying your file. So remember, text editors, nerd war, pick one. It's fine. Nano, very simple. I can show you what that looks like. So you just say Nano on a file, like I have when I have a file in here, I believe. Oh, I'm back. Here we go. So Nano is just a simple. You can use your arrow keys to move around. You can just start typing whatever you like. Backspace. Yes.
Is it possible to add color depending on the language you're using for Nano?
No, for Nano, no. It's very basic editor. To exit, it's just Control X, and then it'll ask you, do you want to save? And I'll just say no, it's fine. But you can use Nano today in the examples. If you're already comfortable using VI or Emacs, you feel free to use that too. Just the short thing is pick a editor and become proficient in it. That's the easiest thing to do. Just pick one and go with it. You can tell I didn't write this part of the slide because VM is terse and Emacs is powerful. I would say maybe the other way around. You do want to pay attention to the cross-platform issues like I talked about, using the DOS to Unix utility if you're using Windows and you're writing stuff on Linux. Careful with using WordPad or Notepad. I just recommend writing everything actually on the machine. Remember that the file names are case sensitive even though they're not on your Mac or your Windows machine. And be very careful with having blanks in the file name. Try not to do spaces. Use an underscore or a dash or something to put in between so you don't have to use spaces. And yeah, do not use Microsoft Word to create job scripts. And also something to note, because I'll probably send you PDFs, don't copy and paste from PDFs because they tend to change the character set. So for instance, I might have a command that has quotes in it, and the PDF will typically replace those quotes with a UTF version that's maybe the slanted quotes, something that looks nicer, but that doesn't work. So don't be discouraged if you're trying to copy and paste from a PDF. Just kind of look through it and write it out as you would. So let's take a look at Stampede. Stampede is composed of 6,400 blades, which we call a node. You probably refer to node in a lot of ways, but we'll call a Stampede node a blade. And those are Dell PowerEdge 8220s, also known as the Zeus nodes. They're pretty awesome. We'll take a look at them this afternoon when we go in there. But basically, they contain 2 sockets, the hard drive, the memory, and enough space to hold 2 Xeon Phis or GPUs. So pretty good size. You can see they're pretty deep in terms of the size, and we'll get in there and take a look at them too. Each blade has, like I said, 2 sockets of Sandy Bridge. Those are the processors that are on there. Each processor is 8 cores, so we have 16 cores total on a node, and then we also have at least 1 Xeon Phi in every node. Some nodes have 2 Xeon Phis. Some nodes have a GPU and a Xeon Phi. But at least 1 in every node, connected through a PCI slot. 32 gigabytes of RAM available on these nodes, so lots of memory, lots of cores, and then of course the Intel Xeon Phi coprocessor, which you'll hear people call a mic or a Xeon Phi, or even sometimes a Knight's Corner. It has a lot of names as it's gone through its history. It's 61 lightweight cores. Again, these are basically like very simple x86 cores. There's 8 gigs of RAM soldered onto that board inside the card, and each core has 4 hardware threads. So you can do a lot of parallelism on these things. And actually, what's really neat, and I think it's pretty cool, is this mic runs its own lightweight Linux. It's actually running BusyBox, which is an embedded OS based on the Linux kernel. So you can kind of think of the fact that when you log into a compute node, which we'll do in just a little bit, there's another computer inside of that computer that's operating this Xeon Phi. So some of the basic specs, like I said, 6,400 of these Zeus nodes in 160 racks. The typical nodes are 16 cores divided over 2 sockets with 32 gigabytes of RAM, 61 cores on that mic coprocessor with 8 gigs of RAM attached to that. And then there's specialized nodes as well. We have 16 large memory nodes, which have 32 cores and a terabyte of RAM. So you got some really big data stuff that's threaded only, doesn't parallelize well. It's a great place to run that. And then we also have a handful of 128 of them with GPUs, those NVIDIA Kepler 2s, and a mic, which are pretty cool. The login nodes do not have mic coprocessors, but that's not a big deal because you can still compile for the mic on a regular node. The nodes do have personalities and purposes, of course. So this is some of the kind of understanding how the supercomputer works so that you don't get banned or get suspended for using it improperly. When you come in through the internet through SSH, you're going to land on a login node. For instance, login 1, or as I'm here, I'm on login 2. There's several login nodes. I think we're up to 8. So they kind of share the load. as people are coming in. And you'll just round robin through them. So if you SSH once, you'll get 1. You SSH again, you'll get 2. But the file systems are all the same. They're all mounted that way. But you're going to hit this login node, and this is where you can write your code, you can compile your code, but don't run your code. We call these the front end or head nodes or login nodes. And again, you don't want to run code there because you're sharing that resource with a lot of other people. What you will do is you'll use the job scheduler. It's called Slurm, and we'll use a job batch script to submit our code to the back-end compute nodes, which you have over here. And again, 6,400 of those guys. And when you actually launch a compute job on these nodes, you get the node exclusively to yourself. You're not sharing it with anybody else. It's just yours, all 32 gigs, all 16 cores, and the Xeon Phi. So pretty cool. Just be aware when you're logging in, remember you're on a head node, and that's shared. When you submit a job, that's yours to do what you want with. So what does that mean? Don't run parallel jobs on the login node. Typically, it's not possible. It will tell you, hey, you can't do this. You can't run these kind of jobs. Or what will happen is you will be able to run it, and you'll start to annoy the system administrators, who will probably lock your account. And then you'll have to submit a ticket and say, hey, I'm sorry, I didn't mean to do that. Can you please let me back on? And people will do. So instead, we're going to submit a batch job, and we're going to do that at the end of today. Just a little bit about the machine. So you do want to know a little bit about the hardware and how it operates so that you know how to use it properly. There are 3 main file systems. There's home, work, and scratch. And here's the size limits. We have 5 gigs on home. Again, that's backed up nightly. So if you delete something and you knew it was there 24 hours ago, you can ask to have it restored. Be careful about that, though. There's work, which is 1 terabyte. You have a terabyte of space there, so you can store some of your large codes or your sample data sets, things like that. It's never purged, but it's also not backed up because we don't have the facilities to back up that much data for everybody. And then we have Scratch, which is about 8.5 petabytes. And again, this is just for Scratch work. So when you're running code that does a lot of I/O, you want to make sure you run that out of Scratch. It's faster. It's a bigger parallel file system. There's no quota on there, but it is subject to a purge policy, meaning that anything that's older than 10 days can be deleted at will. We don't ask. We just get rid of it because it's a Scratch space and everybody shares it. We do have a couple of other things, though. We have Archiver, which is Ranch. It's the name of the machine, and this is a 60 petabyte file system full of tapes. I like that it says essentially unlimited. Kind of. It's a big archive system. Basically, the way that works, though, is these are actually put onto magnetic tape, so it is a little bit slower than you would normally think when you're just moving files around. There's a disk cache in front of it, so if you copy files on, it copies onto a hard drive and then slowly migrates to tape. Same thing when you pull it out, you have to stage the data first, which tells the robot to go grab your tape and put it on disk so you can copy it. One last piece, too. There is a local hard drive on each of these compute nodes, and it's mounted as /temp/TMP, and you get about 80 gigabytes per node. So if you just want to do some local writing, you don't want to mess with the parallel file system, you can write stuff there. Just remember to move it off when you're done writing your code, when your code's done running. Otherwise, it just goes away. Because again, that's purged after the job is finished. From any CPU host, there's a couple of cool shortcuts you can do. We have CDH, CDW, and CDS. These will change to your home, work, or scratch, respectively. On the mics, there are file systems, but the aliases don't yet work fully. So you just kind of CD to the full path. You know it's work, your number / your username. Just do it that way. But again, you can use these shorthands instead of using the environment variables when you're on the machine. We talked a little bit about file transfers. So yeah, SCP and rsync. I showed you the recursive flag using R, and we do recommend reducing that if you have a large file or several large files or lots of small files. because it can be overtaxing on the system. So we should use the tar command to bundle those all into a single archive before shipping it over. Try to avoid doing a lot of transfers at once on the login nodes. 3 or 4 is okay, but any more than that, and the system admins will say, hey, there's somebody that's using too many tars, too many CPs off of the system, so they'll ask us to contact them and say, hey, please reduce your usage. Because again, it's a shared file, it's a shared system, and you're on there with lots of other people. Compression is rarely necessary when you're moving stuff around here. We have so much pipe that you're just wasting time compressing. If you're, say, moving stuff from Lone Star to Stampede, you're just wasting CPU time compressing it, then moving it, then uncompressing it, when really you could have just moved it in a shorter amount of time. So typically don't do any compression. And like I mentioned, on Ranch, staging from tape does take a little bit of time. It doesn't always come back immediately because there may be lots of other people who are requesting data off of the tape, and again, it takes a little bit of time for the robot to get over there, pick up the tape, and read it. Like I said, beware of the cross-platform issues. Spaces, capitalization. Just keep an eye on that. So let's talk a little bit about actually doing stuff on this machine. Now you know a little bit about the hardware. You know what it looks like. You know how it's configured. We have a system here called LMOD. This is the TAC module system. It was actually developed from an earlier open source project called Software Modules. Dr. Robert McClay came here and said, modules are great, but I hate the way these work. Basically, modules allow you to have lots of different software installed, but not have it all in your path. Because we install a ton of software on this machine because we support a lot of different users, right? Lots of different domains, lots of different software. So what we do is we package these all into modules where you can load them when you want to use it. Some software is available both from the Linux installation and as a module. Things like Subversion, Python. You'll see when you log in, you have Python, but if you load the module, it's very likely to be more up to date and packaged by us. So Python, for instance, we do have the system installation of Python. Like I said, it's in user bin Python. But if you load the module, you'll get the newest version that's compiled with that uses NumPy and SciPy, and all of those are linked with MKL math libraries. So it's highly optimized, and it's usually within your best judgment to use those. You can load modules interactively. So if I log in, I can say, "Hey, load the module." You can load them in job scripts. So we're going to write a little job script, and you can actually put in the module load command right in there. You can also put them in your startup scripts. But the easiest thing to do is to use the built-in module set default. I'll show you how to do that too. So why modules? Well, some software you need permission to use. So we do have some licensed software like Abacus and VASP. And so we don't just make it available to everybody. You have to request to be able to use it and prove that either you're from UT or that you have a license that allows you to use it. Also, dependency management was a big problem that we had with the original software modules. We have multiple compilers, so we have multiple versions of the Intel compiler. We have multiple versions of GCC, and then on top of that, we have multiple MPI stacks. We have OpenMPI, we have MVAPitch2, and we have multiple versions of MVAPitch2. We also have Intel MPI. So the management of that is really difficult for all of these users, and this is why modules kind of makes it really nice and easy for you. You can just load the right thing, and it does it all for you. Using the wrong combinations can give you interesting errors, things that would be very hard to track down. So we provided this new LMOD system that basically fixes those problems for you. It doesn't allow you to load two compilers. It doesn't allow you to load the incorrect MPI stack with the compiler that you have. And if you do a swap, you swap out your compilers, it'll go through the list of modules you already have loaded and make sure that those are the correct modules also. LMOD's not on the mics themselves just yet, but that is something that we're looking forward to doing. There's some key commands that you'll want to use when we're looking at the module system. Module help, how do I use this module? That's one you'll see a lot. So maybe, for instance, you are interested in using HDF5, right? Because you're going to write a code that's going to use HDF5 to write all your output files. We can do module help HDF5, and we get a nice little help file that says, hey, when you load this file, we set these environment variables for you to use this library, compile with this option, and then add the following options to the link step. So it shows you exactly how to compile it on our system. And these are things that we write here as the HPC guys at TAC, so to make sure that these things work. And then we give you a little more information about it too. Hey, maybe this option isn't required, but we recommend it. You know, it also tells you the version. So you can also do maybe a couple of other things. Maybe you just want to see what modules you have loaded. You can do a module list, and this just shows you exactly what I'm loaded. I pretty much have a default set with a couple of extras, MBAP-H2, the Intel compiler, TAC paths. These are some of the basic things. Maybe you're interested to see what exactly is on the system. You can do a module avail, or just AV, because we don't want to type that much. And this basically shows you everything that's available based on what I have loaded right now. So we have things like R, Amber, lamps, many versions of PETC, lots of other cool stuff too. RStudio, compilers, lots of different bioinformatics packages, CMake, CUDA, all sorts of stuff. So just the again, the module avail will show you that. And there's a couple of shorthands too. I showed you module list, where it shows me what modules I have loaded. I can just type ML, and it'll do the same thing. Again, more shorthand. Nobody likes to type. So you can do ML to just list. If you want to load a module, you can say maybe ML HDF5, and the shorthand version of how to load that module. So you have help, you have load, and then a module name. Avail shows you everything that's out there. Unload will remove. You can also use module del or delete. You can also say module minus and a module, and it'll remove it for you. There's a lot of different ways you can use it. Say I wanted to change my compiler. Well, our module system is smart enough that I say, oh, module load ML GCC. It says, you know what, you can't do that because you've already got the Intel compiler loaded. It gives you a nice warning, and then it even tells you how to do it. You need to swap your compiler because you can't have two loaded. Spider shows you all modules that are available, and then you can also say, maybe I want to see all the versions of something that's available. Like, I know we have GCC, so this is the thing. If I look at the system version of GCC is 447. If I do a module avail GCC, it shows me that I have 3 different versions available of GCC, and all of them are newer than the system version, right? And they're also probably include other cool stuff like an OpenMPI and things like that. So you can the one with the D here is labeled as a default. So if you just say GCC, you'll get that one. Let's see. Yeah, again, abbreviated versions, ML module, and then module reset. If maybe you loaded too many things, you don't know where you are anymore, you just want to go back to default, you just type module reset, and it'll just do system defaults. A couple other things I find very useful for people is sometimes you log in and you're like, I always want this module loaded. I don't want to type module load NAMD or whatever package it is that you use all the time. What you can do is you can just load that module, like maybe FFTW3 is something I use all the time. I always want it available. I just type module load FFTW3 or ML FFTW3 and then module save. And what that does is that creates a save file in your home directory so that every time I log in, all of those modules are loaded for me. It's a nice way to keep your default set. You can also save collections of modules, maybe if you're working on multiple projects that use different pieces. So maybe I have just my chemistry tools, my chemistry toolkit, I load all that stuff and say module save chem tools, then it'll save me a .modules file that allows me to just load those things. And you can just do module restore the name, and that's pretty nice. A great way to achieve reliability and repeatability. Absolutely. So currently, the Intel version 13 is the compiler of choice for Stampede. It's the only compiler that supports Xeon Phi coprocessor. Well, we have version 14 that also supports it, but the default is 13. There's currently 3 versions of the GCC suite available. As I showed you, I did a module avail on GCC. And we also have other specialized compilers. For instance, we do have the CUDA compiler installed because we do have Keplers on there. You can just do a module load CUDA and you'll get NVCC. And of course, this is not entirely correct. The compilers are available on the login nodes and the development hosts. So if you're in the development queue, you'll have compilers. But if you're on a regular compute node, you do not. So you do want to be cautious. When we do the lab later on today, I'll show you that we're going to compile and then log into a compute node. Their compilers are not on the mic coprocessors, but again, you can compile for mic on the regular host and on the login node. There's a ton of math libraries available out there, but of course, MKL's mic support is some of the best right now. It is an Intel product. So there's some cool stuff you can do with automatic offloading of some algorithms, and then of course you can just run stuff right there on the mic as well. So when we're compiling some MPI code, and we're going to do this today, you just change up the compiler command a little bit. For C programs, it's MPICC. For C++, it's MPICXX. Fortran 77, MPIF77. Fortran 90, MPIF90. So the typical compiler commands, if you're just using the Intel compiler, would just be ICC or GCC if you're using that, and iFort for the Fortran stuff. The MPIF90, what that does is it wraps the entire command and all of the things that need to be linked in there for you, so you don't have to remember all of the stuff. For instance, if I type MPIF90 minus show, you'll see that this is actually what that command does. It runs iFort with all of these libraries linked in and all of these links, and then whatever you're doing. So it's a nice shorthand. I'll show you what's going on there. And of course, again, you just compiler, some options, your program. And we'll do an example of this in just a minute. So your ticket to compute nodes, if you want to actually run some stuff, you can go to get to the backend compute nodes. You can use sbatch, and we'll write an example script today. If you want to do an interactive session, which I know everybody does, you want to get on and start playing around, running and writing and running some code. You can use this command called idev, and it just submits a job for you and kind of auto-magically logs you into this compute node, so you can start playing around. Other ways you can get on the compute nodes, if you run special applications that connect to the back end, DDT is a parallel debugger that does this for you. You can also, if you already have a job running, you can SSH to that node. I know I mentioned that you get the node to yourself. We call that exclusive access. So when your job's running, you can SSH to that node and do whatever you want with it while the job's running, but nobody else can. And once you're on a compute node, you can actually SSH to the mic or the Xeon Phi by just typing SSH mic 0. And I'll show you what that looks like today. If you don't use sbatch, then you're running on the front end or login nodes. Don't do that. That's the word of advice. Don't launch any executables from the login node. Don't run an a.out. Don't run your simulation code. It is, like I said, one of the easiest ways to get your account suspended. And like I said, we do have admins that are on there all the time going, this guy's using too much, turn him off, and then wait for you to submit a ticket, or we'll contact you. So Slurm, like I said, is our resource manager, our scheduler. So when you want to run stuff on the back-end compute nodes, you submit a job to the scheduler, and the scheduler gives you a node when one's available. To launch a batch job, you use the command sbatch and then the batch file name. And I'll show you an example batch file name, and we can do one together. If you want to launch an interactive session, you can actually just type idev, and it will probably figure out what you need. For most of you guys, you're only on this one allocation called 2014 REU. So if you just type idev, it'll put you on the development queue for 30 minutes using that allocation. And like I said, the A flag is optional unless you have multiple projects. So like in my case, Reese, I have like 12 projects. I always have to use the A flag to make sure it charges against the right account. If you want to view all the jobs that are in the queue, you can use the SQ command. You can pipe that to less or more so you can see what's going on. Or you can use a command that we ported called show queue. So if I do SQ, there we go. SQ, we can see there's lots of jobs sitting out there. And again, I just let it kind of run through there. Show queue gives it a little more cleaner output. So we can see just what jobs are running, what jobs are waiting. These are all the waiting jobs that are blocked because they're maybe waiting for dependency. These are all jobs that are just in the queue right now waiting, and you can see who submitted it, what the job name is called, how many cores they're requesting, and when that job was submitted. And then we see up here, we currently have 96% of the machine running, so there's a lot of jobs running right now. 819 jobs on 6,196 of the hosts of 6,400. And then you can see here, you know, some of these people are running just 16 core jobs. Some of them are running like this one. He's running an 8,000 core job. That's Carlos. He's probably doing some benchmarking. And we have some bigger ones too, running 1,300 cores. So just kind of a nice view of what's going on the machine. So you're not wondering, hey, I just submitted this job. Why is it running yet? Well, there is a queue, and there's a lot of people in line. So don't always expect that everything will run immediately. Now, today when we use the development queue, we should all be able to get in. If we don't, we can jump on the normal queue. Because typically, if you run a short job, like less than 30 minutes with one node, you'll get in pretty quickly. Of course, you can't do a lot other than just kind of do a demo, but kind of nice to see that. If you can see your own jobs by doing SQ-U and putting your user ID in there. It'll only show you yours instead of the entire machine. And if you submitted a job and went, oh, that's not exactly what I wanted to do, it's the wrong code, or it's got the wrong input file, you can use scancel and the job ID. And so this is the first number is the job ID, then the job name, and then the user. So you just scancel and that ID. Yep. I'm sorry?
When we type in our user ID, we have a problem with that. Greater.
Yeah, no, you don't need those. That's just to represent, to replace your user ID with that. So currently I don't have any jobs running, so if I do SQ, it'll say, hey, there's nothing there. You can view the status of all the queues too. If maybe you're sitting there saying, man, my job's been waiting for a really long time, what's going on? You can run sinfo. So let me see if I can do this. sinfo -o, what's the format? %20p, %5a. And what this will do is this will show me what the status of these queues are, and currently they're all up, meaning that they're on. Sometimes queues will get disabled if there's problems with those nodes. So this is a quick way to see what's going on in there. If you are looking at the queue limits, you can ignore them in this command because these are not the ones that are being used to enforce the queue limits. We have a lot of queues on Stampede. Like when I was showing you the hardware, we have a lot of different pieces, right? You have a normal queue. You can run up to 48 hours in that queue. And up to 4,000 cores. Okay, pretty simple. Use this for normal production, regular old things. You're running all your regular code. You're not using any mics. The charge rate is 1, so meaning that you get charged 1 for every core that's on there times the hours, and that's how the service units are calculated. So if I use 1 node for 1 hour, I've used 16 service units. The development has a max runtime of 2 hours. Maximum of 256 cores, and I believe you're limited to 1 job at a time in the development queue now, which is good, so it allows a faster turnaround. And again, this is just for development. You do have compilers over there, so if you're playing with code, you need to make some changes and try to run it, that's the place to do it. We have the large mem queue. same thing, 48 hours, up to 128 cores. The charge rate is double, though, because there's a terabyte of memory in there. So it does cost a little more in terms of your SUs. We have a serial queue as well with a maximum time of 12 hours. You might use that, maybe. If you're just running simple serial jobs, you can put some stuff through there. We also have a large queue that allows you to get up to 16,000 cores. You do need to request to be added to the large queue if you're going to run something like that. And basically, we just ask you to demonstrate that you can prove that you're scaling really well up to 4,000 cores. And if so, then we'll put you up into the large queue. If you want to start using the mics, you just submit to normal mic. You get 24 hours of runtime, up to 4,000 cores, and you'll get all of those Xeon Phi happiness. We also have a GPU queue, up to 512 cores, and of course these are the nodes that have the Kepler K2s on them, K20s, and we have a GPU dev, which is just 4 nodes that are available. So if you actually want to maybe run and compile stuff in the development queue with GPUs. And then we have another one called the Viz queue. It's maximum 8 hours. It's designed to be interactive so that you can get on there quickly and you can run a VNC session to those nodes so you can do visualization of your data, which you'll learn a lot about over the next couple of weeks. So here's a basic MPI job script, and I'm going to show you, we're going to just pull one off of Stampede that we've created for you, but I wanted to give you a little bit background so we can touch on this. This is the most important part right here is don't miss this line. This is a bash script, so you just shebang bin bash is how you read that. And this is just a generic MPI script. You laugh, but that is what they say. This is a shell or a sh, and this exclamation is also referred to as a bang. So it is shebang. So just a generic MPI script here. This is going to be set up to run on 2 nodes with 32 MPI tasks. The first bit here is the -cap_j, which is your job name. So as you saw when I ran show queue, you saw there was a job ID and a job name. That's where that appears. The O and the E are for your standard error and standard out. We talked a little bit about those, about how you can write to the different streams. And what this does is this puts it all into a file in the directory that you run for the standard error and the standard out. The -P is for which queue you want to use. In this case, we're going to say development or maybe normal or normal mic. And then, like I said, this big N is for how many nodes. So it's 2 nodes, but each node has 16 cores. So when I say 2 nodes, I'm going to use 32 MPI tasks. Last bit, -T, gives me the runtime. How long do I want this to go for? In this case, I'm just going to say 30 minutes. They have some cool stuff too, where you can actually have the system mail you when the job starts or when the job ends. So maybe you're waiting for a job to start and you want to log in and see what happens while it's going. Put this in. You can mail type all. We'll send you an email right when the job starts, so you can go, okay, cool, it's on. Get it on your phone, something like that. It'll also email when it's end, so you can say, cool, my job finished. I'm gonna go take a look at it now, rather than, is it done yet? No, okay, I'll come back later. Last part here, if you have multiple projects, you do need the -A. Again, most of you guys are going to be on, you're just on 1 allocation right now, but you'll probably get added to your research allocation soon. So you'll be on 2 of them, and you'll need to use the -A. You can, as I said, use module commands inside of your batch script. So maybe you want to load FFTW. Maybe you want to do a module list so that it shows in your output file what modules you had loaded when this code ran. Reproducibility is kind of an important thing. And then for MPI codes, you'll type IB run and then your executable. And that will do all the magic behind the scenes to launch your MPI job. If you're just running serial code, no MPI, just a simple C or Fortran code, you don't need the IB run. You just run your a.out or your executable. The stack is always under construction. This is true. We're always building new software and changing things up. So it's always good to take a look at what's available, make sure what you have loaded is still there. We are actively working on R, Octave, PETC. These get updates a lot. If you load the Python module, you get access to NumPy, SciPy, and Matplotlib. These are all very useful tools if you've used them. If not, you should definitely look them up. They're really nice. We also have analysis and debugging tools such as Tau, PAPI, PerfExpert, DDT. These are, again, just debuggers or analysis tools. If your research associate says, hey, can you profile my code for me and tell me where it's slow? You can go, yeah, we have these things. We have some other cool things that were developed here for parameter studies called the launcher or the PyLauncher. And these are just basic programs that say you have a single code and you want to run it over hundreds or thousands of different input files, single program, multiple data type stuff. You can use these tools to actually launch them all simultaneously rather than running one at a time because they're just serial. If you try to add 50 jobs to the queue, they're not all going to run one after another. They're all going to sit in the queue based on priority. So you can kind of package them all in together using these tools. And we'll talk about those tomorrow during the scripting talk. There's also all the high-performance file I/O packages, HDF5, like I showed you, parallel HDF5, NetCDF. And of course, you can build and install your own tools. You're not restricted to only the things that we provide. You can also build whatever you like. I recommend installing them in Work because you have a terabyte of space there. Download the tar archive, not a prepackaged installer. And the standard trick on most Linux installs is to, when you do your configure, do a ---- prefix equals wherever it is you want to install it. And in this case, I'd say install it in Work and maybe put my apps or something like that. I have a Work apps in my folder in my directory too. If you're kind of get stuck and you don't know where to go, you're trying to install it, and nothing's working, you can submit a ticket and say, hey, I'm trying to install this package, can you help me out? And there will be somebody on the other end that will lend you a hand or at least give you a couple of tips on what you might need to do. A couple of keys to good citizenship. Like I said, and I'll reiterate, remember you're using a shared resource. The login nodes are shared, the file systems are shared, the bandwidth is shared. So use the components for their intended purposes. Compile on the login nodes, run on the compute nodes. Appropriate use of login nodes, building software, but compilers are also visible on the development nodes, but typically build software on the login nodes. Manage your files if you're moving, editing, transferring. When you're submitting, monitoring, managing batch jobs, you can do all that on the login node. You can launch interactive sessions from the login nodes using IDEV, DDT, etc. And maybe some light post-processing, like maybe if you're just generating some plots in GNU plot and it only takes half a second, doesn't use a lot of resources. That's something you can do on the login nodes. Inappropriate use, don't do science on the front end. That's as easy as we can make it. Access the compute nodes with IDEV or SBatch. Don't launch your executables on the login node. Also, avoid simultaneous instances of demanding processes, like parallel makes. You can do make-j and tell it to use multiple processors. Don't do that on the login nodes. You can do a single make, maybe two, and then tar and untar. Keep those to about 2 or 3 at a time. Try not to load up the system with a bunch of tars or transfers. A couple of other points. You do want to avoid running jobs from your home directory because it's not as big or fast as Work or Scratch. And again, there's a lot of people in home that are trying to write code or move stuff around. So avoid running from home. You want to run any I/O demanding jobs out of Scratch. That's the best place to run your code if it does any sort of I/O. Run it out of Scratch. Avoid frequent I/O if possible. So you may have a code that says, I'm just going to dump all these files every couple of seconds. That's bad. If you can rewrite it or tune it so that it only dumps files maybe every hour or every half hour or something, much better. You want to minimize the simultaneous I/O from many processes too. So don't launch a 4,000 core MPI job and have them all open a file and write. Probably a bad idea. And then, as you're playing around and you start working with this machine, start to learn and recognize the other other things that cause stress on the machine. Like, for instance, doing an ls on big directories. It can be bad because if you have millions of files, every time I do an ls, the first thing it does is it stats the directory and says what's in here, and then it says that's a file, and it stats that file again and says what kind of file are you. So when you have a directory with 1 million files in it, it's going to do that twice for every file. And that can be taxing on the system. So one thing I like to do, as I showed you the, if I'm in Scratch, I'm going to use CDS. If I do an LS, I get colors. But let's say I had a lot of files in here. What I would tend to do is do bin ls. Now you see I don't get any colors, and it's a little less taxing on the system. It doesn't have to do the double stat. Also, you know, as you start working, learn when it's time to use parallel I/O, and you will. You'll find it. You say, man, this is rough. I really need to work on this. So let's do a quick lab. I'm going to give you some files. You're going to grab these files off of Stampede. We're going to run an MPI batch job. That's just a simple MPI code that we can look through. We'll run an interactive session using IDEV. And then we'll also run a mic application and visit the mic, just so you can kind of get familiar with it, check it out. So, yeah, I'll email those around. I'll give it to Rosie and make sure she gets them to everybody. Alrighty. Let's get to this lab. There we go. Lab. All right. So let's get everybody onto Stampede. Is everybody logged in already? Excellent. So you just SSH with the username. Go ahead and change to your work directory by doing CDW. And I'll do this along with you. CDW. So now I'm in my work directory. If I type pwd, you'll see that I'm there. Yes. Are you logged into Stampede? No, that'll happen. So again, CDW, and then if you do it, type pwd, you'll see you're in your work directory. If you do a module list, or just ML, you'll see all of the modules you currently have loaded. So, for instance, I got the Intel compiler and BAPH2, a couple of other things. Now we want to untar the lab file that's in this user called train00. It's in his directory. So if you write this command just as you see it, tar space xvf tilde train00 slash lab1.tar. This is gonna grab this tarball from that directory and open it up in your work directory. And you should see some output similar to this. Uh-oh. Dropped out of the call. Yeah. I apparently logged out somehow. Let me join me back in here.
Where's that little,
There we go. I'm back. Dropped out of the call there for a minute. Okay. So everybody's got the tarball in their directory, right? And they see something like this. Now what you can do is you can change into that directory, lab 1, cd lab 1. And now if we do a pwd, you should see that we're in our work directory, in the directory called lab 1, right? Everybody's with me? Excellent. If we do an ls, we see that there's a handful of files in here. What's that?
What do you do before L?
I just did a PDW to make sure it was in that directory. PWD, sorry. So you're here in this directory now? Did you untar the file first?
Oh, I did the tar. I got a bunch of
Thank you, sir.
Override an existing file, is that?
If there was a lab 1, yeah.
Yeah. Some of these machines may have overwritten. It's your system or is it?
No, they're all on Stampede.
yeah, I did.
The lab 1? You're in there. You look good. You have CD into that lab 1 directory? Change into the lab 1 directory. CD space lab 1.
Oh, I guess I'm gonna need a lab 1.
Now doing LS.
Oh, I get it.
There you go. Good, you're good.
Oh, I get it. I was looking at the dollar symbol and I got confused.
It's okay. That's just my prompt.
Yeah.
Okay, so now that we have that, what we can do is we can compile this program called MPI-Pi. And this is how we're going to compile it. We're going to call MPI-CC, and then the code MPI-Pi.C, which is a code that we supplied for you. -O means change the output file to be called MPI-Pi.
Is there a space after the
No, no spaces in the word. So everybody has a compiled program now. MPI-CC of this program called MPI-Pi.C. -O because I want to change the output file. I don't want it called A.out. I want it to be called something. I want to call it MPI-Pi. There we go. So now if I do an ls, I see I now have this executable called MPI-Pi. Groovy? All right, now we need to take a look at this batch script that I wrote, lab1.batch, and we need to make some edits to it. So use VI or Emacs or Nano, whichever you're comfortable with. If you don't know any of them, I recommend Nano. So I'm going to use VI, and we're going to take a look at this lab1 batch file. And I can tell you probably can't read that, but you can see it on your own screen. What's that? Nano. If you don't know an editor, use Nano. Nano, the file lab1 batch. This will open up your job script, just like the one that we saw earlier. You look puzzled. Ask questions. Help your neighbors.
After the good.
What's that? Yes.
Oh.
Yeah. Yeah. That's where it's from. All right. There's one thing we want to change in here. The first thing we want to, the one thing we want to change is this charge code here. We want it to say sbatch A, and we want it to say your allocation, which is 2014 REU. So again, I just changed this guy. No, there's no mouse in the editor. You just use the arrow keys.
Oh, okay.
Yep. And you see there's one below it with a couple of pound signs. That's actually a comment, so it's commented out, the one below it. All right, everybody's got one of those? Excellent. So we don't need to change anything else. Basically what it's going to do is it's going to run the date command, and then we're going to IB run this executable that we just created, and it takes an input, which we have here. So we can just save this. If we hit Control-X in Nano and say, yes, save this, you just hit Enter to give it the same file name.
Control-Enter again.
I'm sorry? Control-X to exit. You see the commands on the bottom? Okay. All right, now that you all hopefully have a batch script here, let's go ahead and submit this. sbatch lab1 batch.
When you see the file names, right? You save it as
You can save it as the same thing. Just hit Enter. And you should see this kind of output. Welcome to the Stampede supercomputer. Does some validation. Make sure that you're on a proper host. Make sure that you have a job name. Make sure that you have directories available. It just does some sanity checks to make sure everything's cool. And if you now do SQ and your username, you'll see right now my job's running. It's in the status R. And it won't run for very long. It's a pretty quick program. But if you do, you guys see your jobs are running as well now?
Yeah. Why does he
What's that?
Yeah, when I try to copy it, I'll copy yours, and it says command.
Oh, that's my prompt. Remember in the beginning I changed my prompt so that it shows me the directory I'm in? This is just my prompt. Everything after this is the code that I'm actually typing. Yep. Yes?
So anything after $, is always.
You got it. Oh, you're in BI. Okay, hit escape. You're not on.
That's not. We just got like.
You're just gonna have to restart a new session. It disconnected.
I mean, something.
All of this is.
Yeah. Yeah. This is.
Yeah.
Now you can do batch. I think it said yes.
2014 REU. These are commands down here. Wait, save. Can you try? This is what name, just leave it as is, and then formula's just overwrite the existing file. You can submit it, just attach S batch, that one batch. You get yours in?
Yeah.
Yeah. Yeah, you got it. Yes.
Sorry.
You can't use your mouse. You can't use your mouse. So, mouse down. Just leave that up.
Go back there.
There you go. Backspace those.
This guy, that's been for long, 2014.
For lunch?
Yeah.
Show you.
And you're good, so now you want to save it. So you see these on the bottom, these are your just Control X and exit. So it says you want to save it. Yes. And then enter to save it as the same file. And now you can submit that batch job by typing S batch and then file. So that's you.
So like downtime, like, people not have too much for. Well, but like you can only scroll so much. Or
file. So they were actually hanging off by their. They were. They tried to save my other guy.
So that stuff's in the slides too. So actually copy those. You don't have to write it all down. Go ahead and submit that now so you can see it.
I had a tab. It's like a watch. I was trying to like my friend to get me. See that file? That's
Got it.
I think that's the second one. You can't see the skins over it, but
Okay.
hit it really hard. Not purposely. You have to shoot what you're walking about. And end up cutting it. And so when I put prosthetic on,
And then right now, what you do, you can open up minus U. See that last command I tried? SQ minus U and then your username.
Thank you, and I'm second.
Yep.
Oh, okay.
Yeah. There you go. You see pending. So it doesn't run yet. It's like. Looks good. Good. Running. Excellent. Okay, I think most people should have it run already, right?
I mean, it's pending.
You're pending? Mine's done. Check again.
Yeah, I've been checking.
Okay.
So,
Got a couple through? Excellent. And what you'll see is now I have these error file and an out file. And what I can do is I can just use less to just look at these, right? I don't need to edit them. So let's go .out. And there we go. This is the output from the program. It started up the task, and then it computed the value pi, calculated my absolute and my relative error, and told me how many MPI processes it used. So what this program does, and we'll look at it afterwards, is it's basically taking pi and splitting it up over and doing an estimation using Riemann sums. Fun stuff. Do an LS first. Make sure your job's finished. And it doesn't look like it's run yet, so you gotta wait for it to run and you get output files. So if you do the SQ minus U in your username again, oops, let's catch that. Pending. So it'll take a few minutes sometimes because it is a queue and there's other people using it. So it'll take a little while, but I just wanted to show you what that looks like, and you'll be able to take a look at that. Those will stay there for you. Okay. Yeah, I was just taking a look at I did an LS and I said, hey, here's my error file and my out file. My error file shouldn't have anything. Just the date and that I ran the command that I ran. And then, like I said, this is the .out. That's the output. And again, we set that when we were writing the batch script. Remember, we wrote these two lines here. Where to send the output? That doesn't help at all. Where to send the output and where to send the error. Here. Lab 1 batch. No. Right here, where I set -O was my MPI, my program. %J says use the job ID. So if I run a lot of jobs, I know which one goes to which. So here's the output file and the error file. And again, when your job runs, you'll see these in your directory. Oh, and I can't use Nano. All right. So that was pretty cool. We can take a look at that stuff. In the example here, it says use more. You can use less. You can use cat. You can open it in Nano. It doesn't matter. Right? There's a lot of different ways to do that. The next thing we want to do is do an interactive session. But we're going to do this a little out of order because the way this is written is incorrect. Oh, no, it'll work. What you want to do is just go ahead and compile this Fortran code. We can do that right on the login node here. So we'll say, here we are, and here's my hello.f90. And I will just say ifort for the Fortran compiler, ifort. And I had some options on there, right? OpenMP minus OpenMP. And we're going to talk about some of this stuff later on, too. What is OpenMP? What is MPI? And this is just an introduction to get you guys running. So hello.f90 minus O, hello. Give it a file name. So again, here's the whole command. ifort space minus OpenMP space hello.f90 space minus O space, give it a file name like hello. Yeah, you can call it whatever you want. If you don't put anything on there, it'll just call it a.out. Did you type ifort? Are you on Stampede?
Would G4 also work?
G4 would also work. Absolutely.
Is there really like any kind of give or take with which one you use between G4 tran and I4? Like, is one's like preferred in some instances over the other?
Yeah, the Intel compiler is highly optimized.
Okay. So really there's just stuff
if you don't have a license.
Fair enough.
Oh, we have licenses, so,
Yeah.
so it's okay. But yeah, you can install those on your local box if you just install GCC and G4 with apt-get.
Yeah, sudo apt-get.
Yep, just sudo apt-get and you'll be happy. Yes. Where did you type? Sorry, where are you? That's okay. Did your job ever run yet? Did you SQ your name? It's still pending, so that hasn't finished yet. It's okay. Remember, it's a busy system. There's a lot of people on there, so it'll make you wait in line. It might not run for a few minutes. But what we can do now is we're running the next one, which is just in the same directory, type I4. That one's not a command we need to start with. Remember, this is just my prompt. My prompt is everything is jlockman at login2:lab1$. Space minus open MP, all that good stuff. Same problem.
Yeah, mine's good. I just. Oh.
Syntax. You good? Cool. Okay, for those who are ready to rock here, let's launch an interactive session by typing idev space minus p normal, because I think we'll have better luck getting into the normal queue than we will the development queue, if there's a lot of people in there right now. And you may need to add the minus a, so let's say 2014 REU. So that's, whoops, again, that's idev minus p normal minus cap a and our allocation. And hopefully you see what I see here, is it said, hey, I submitted a job, pending.
I pressed enter twice, read the last part.
Oh, I didn't write that either.
What's that?
I didn't write that. I just wrote I did and then
That's fine, because if you're only on one allocation, it'll just take that one by default. So is everybody on a prompt now that looks like something like this? Everybody's pending.
Yeah, we all pressed enter.
That's okay. I'll do the demo for you. How's that? Yep. So I'll demonstrate for you. So here I have the lab one, and I compiled that hello world in Fortran 90. And so what I'm going to do is I'm just going to go ahead and run that. Remember, I'm on a compute node, so I can run code. And it's a pretty simple code. It says, hello from the Sandy Bridge host. The value of the number of processors is 16. The number of threads is 1. And I can change these things right now. I'll show you in here. I can say export OMP num threads equal 4. So let me do that. And now if I run this program again, we can see now, hey, the number of threads is 4. Nifty, right? Pretty simple. So one other thing I want to do, and again, I'll just show this to you because we're waiting for a lot of stuff here, if I want to run on the mic, I can run this same code on the mic or the Xeon Phi, but I have to recompile so that I add in the mmic library. So I'm going to go ahead and I'm going to open a new terminal because I can't compile on the compute node. So that's going to be pretty similar. ifort minus mmic minus openmp this hello.f90, and I'm going to call it hello again. And so again, on the login node, I'm compiling a mic code, which is fine, but I actually have to run it, oops, over here. So here I am on my compute node again, and we see I just recompiled the hello. I'm going to go ahead and run that. Oops. No, I'm not. I'm sorry, how do you what? Control C? What I didn't do is I went into the normal queue. I didn't go into the normal mic queue. So I'll go into normal mic and see if I can get in. Maybe I have better priority than everybody else.
Is there priority to users?
I'm sorry?
Is there priority attached to user account?
Mm-hmm. Yes, there is, and it's based on the priority is based on how many jobs you've run. So it's a fair share algorithm.
That makes sense. I got it.
Yeah. So if you just ran like 30 jobs, your priority is a lot lower than somebody else. Okay. So here I am on the normal mic queue, and I just wanted to demonstrate what this looks like. We do hello, and it's going to actually go and run on the Xeon Phi. And so now we see that the number of processors is 244. I told you there were 61 cores, though. So why is there 244 reported? Ideas? They each had 4 hardware threads.
Yeah.
You got it. So that's what I wanted you to see. And then what you can also do is you can actually SSH over to that mic. If I just say SSH mic 0, I'm on the compute node. I can log in over there, and it says, hey, cool, access enabled for me because I have exclusive access to this node. You can do an ls, and you can see that my home directory is here, but I'm actually logged into the mic that's on the compute node, which is pretty cool. Let me go ahead and exit out of there so I'm not hogging the node. And you can, of course, play with these on your own. Like I said, I'm going to distribute these slides for you so you can play along at your own time. You can play around with changing the number of threads and running some of these things. And then, of course, I just type exit to get out when I'm done. And that does conclude the lab and concludes our session for today. So got you out in good amount of time. You can hang out and ask questions. We can do a tour, but if you want to catch that 3:30 bus, you'll probably want to take off pretty soon. We can still squeeze in a tour tomorrow, too. It's not a problem. Okay? Thanks, everybody.
Thank you.